This is R.D. Sharma solution, class 12, chapter 10, differentiability. VSAQ, very short answer questions. Define differentiability of a function at a point. So, we have heard a lot about differentiation, but all it comes from whether it is differentiable or not. Then only differentiation you can do. But everything starts with continuity. Okay. So continuity, if the function is continuous, we can check for differentiability or non-differentiability. So differentiability means a point when we go to the left or right, the tangent or the point of contact of a line, or though the line should be only one. For example, if I draw a line here, if I want to check the differentiability here, then the from positive x-axis, the angle m tan theta dy by dx del y by dx, this is called the differentiation, and the possibility of just one tangent, not two tangent at that particular point, is called that this function is differentiable. For example, if you have certain situation like this, you have a point to check and you get two tangents at a point, just on the left hand side and right hand side. That is called the left hand limit or right hand limit. In the case of differentiability, we call it as a left hand derivative and right hand derivative. Okay. So how do we write it? The basic idea is the base is a function. So you call it as a function that if a fx, a function, it be a real valued function, and this is defined on an open interval a and b, this is a, this is b, and then you choose, or you are given a value c, that at point c you have to check, and this c is belonging to a and b interval. Then at x equal to c, if this fx function is differentiable or derivable, or it has a derivative at x equal to c, then limit extends to c, fx minus fc, of course c is the point where we have to check, fx minus fc divided by x minus c. This expression is the derivative, or it is called as f dash c, and this function, this whole what I have written in the brackets, should be finite, that is, should not be form of any of the form which I am writing. It should be unique, it should give you a proper value, not undescribable or indeterminate value. That is called the derivative, and differentiability is given by the finiteness of this expression. Okay. Is every differentiable function continuous also? See, continuity is all about not picking up your hand and drawing something without a chance of picking up your pencil or a pen. For example, this I am making, okay, I am going through that graph over it, and I don't have to pick my pen up. That is, there is no break. If you can understand by this example that you are on a trip and there is no break. This is a continuous road. There is no breakage. There is no traffic jam. There is no bridge being already fallen off. So when you talk about differentiability, see, differentiability is not what we learn in continuity. Differentiability is all about the slope of that particular point. That is, if that point, if you go on the left, a little bit right, and you get two different tangents at that point, we say that no, this is not differentiable. If you go left and right, that is, if you want to check at set c, then c minus h, c plus h, you find out, and then both the value at this c minus h and c plus h both have the same tangent. that is same value m tan theta dy by dx or y by x or del y by del x, all of it, then we call that the function is differentiable. Okay, there may be functions which are continuous which are not differentiable. Okay, we'll take the example later on. But yes, if a function is differentiable at a point, then it is necessary that it has to be continuous. That is, continuity is not the guarantee that the function can be differentiable or not differentiable. The function can be differentiable, it cannot be differentiable. But the differentiability is a guarantee that the function is continuous. Okay? So continuity describes differentiability, whether it is yes or not, but differentiability guarantees the continuity. The question is asking only about yes or no, so you can stop here. But if you want to prove it, then also we have different options to prove it. I'll just prove it. Okay. So for that, let us consider a function fx, and it is differentiable at x equals to c. Okay. Let us take this point c. Then what is the definition of differentiability? Limit x tends to c, fx minus fc divided by x minus c. This expression should exist finitely, and then we call it as a f dash c. Basically, it's a differentiation only. By first principle you can call it. Okay. So in order to prove that fx is continuous at x equals to c, which I have just taken in that graph, left hand graph, it is quite sufficient to just show that limit x tends to c fx is equal to fc. If you put the value of c in fx and you get a value fc, then it is continuous. That is, you don't have any break. Everything is smooth now. So this thing is sufficient in order to show. Okay. That is, limit x tends to c fx. If you apply this limit on a function f, and then you get fc, that is the value of the function, then you get the continuity. So let us see how to prove it. See, we have limit x tends to c fx. This is what we have to judge, and we will finally prove it to be fc. That is the value of the function at c. So you have fx. See, fx. What is fx? And we will introduce some f dash x here. Just I'll show you how we are going to do this. I am adding and subtracting fc. It will not have any effect. You can just cancel this fc. So this fx can be written as fx. This fc negative fc I am bringing in front, and a positive fc I am taking later. So fx minus fc. You can multiply the numerator and denominator by any number. Why not to multiply by x minus c? So x minus c in the denominator, x minus c in the numerator, it will be cancelled out, and you have fc already there, right? Now let us apply the limit here. When you apply the limit, we just started with fx, we have not done anything else. So limit x tends to c, it will go to each and every value. Here also, limit x tends to c, everywhere. Well, this limit x tends to c on a constant will not work, but still, you need to show that limit x tends to c has to be there. So this fx minus fc by x minus c is nothing but f dash c. Limit x tends to c in x minus c will be what? If you put x as c minus c is 0. Plus limit x tends to c fc. Since fc is a constant, whatever limit you put, it doesn't matter. For example, if you have limit x tends to 2 and you have a 5 value, where are you going to put the x? It will always be 5. So just keep it as fc. F dash c into 0, anything with 0 will be 0. So you get fc. And what did I tell you in the beginning? that if limit x tends to c, fx, if we can prove it to be fc, then it is sufficient for us. So we have proved it. Fx is continuous at x equal to c. You just have to do or prove this, and that will be sufficient. Is every continuous function differentiable? So we just discussed it now. Every continuous function, it can be differentiable, it cannot be differentiable. We don't know that. We have to check. But if a function is differentiable, then the function has to be continuous. Continuity is not the guarantee that the function is differentiable or non-differentiable. But differentiability or having a differentiation or having a derivative is the guarantee. For example, if you take a staircase, continuity come first, then you climb up to differentiability. You don't go first differentiability and then come to continuity. It is always continuity first, then you go up to differentiability. If you have reached differentiability, that means you have already achieved the continuity. Okay? So this example is a very well-known example which we have so many questions on modulus x which we discussed. So y equals modulus x is a classic example of a function being continuous but not differentiable. A function or a graph of the function, if it can be drawn without break. See, if you have a car and this is your track, you don't have to stop. You just have to take a left turn here and just move along. That means you will not have any break in your journey. So this is continuity. But since the peak here is a sharp edge, and if you take on left and right some point, and if you want to draw a tangent, the slope of the tangent at these 2 points are different. That means this function will not be differentiable because at particular point we have 2 different tangents, and that we doesn't want in differentiability. Give an example of a function which is continuous but not differentiable at a point. This is just what we have seen, and we'll prove it just now. And continuity and differentiability you can prove easily. So we have done this question all through. So y equals to modulus x you can have. See, if you have a line y equals x, this is a simple line which is passing through the origin, y equals x. When you take the modulus, that means you cannot have a negative value, negative y value. So negative y value can only be made positive when you multiply negative with a negative. So this line, the below line has to go up. That is how the definition of this function has come. Y modulus x, it will be x if x is greater than or equal to 0, or minus x if x is less than 0. Because once you are below, there will be a negative value. So in order to make it positive, because modulus x will always give you a positive value. In order to get a positive value, you have to put a negative in front of it. That is how it is negative x. Okay? So this modulus function or mod function is continuous at x equals to 0, but it is not differentiable at x equals to 0. I hope you will be able to do it. Okay? So 10.1, 10.2, there are so many exercises, so many questions we have done, and there were more complicated questions we have covered because it was modulus of log of modulus x. That also we have completed, right? So I'll just give you a hint. Y equals modulus x, as I just said, will be x if x is greater than or equal to 0. It will be negative x when x is less than 0. So negative x, x is 0. There is a slight correction I'll make just now. So x equals to 0 will check, left hand limit and right hand limit both we are going to check. We'll go a bit on the left of x equals to 0, so we'll write 0 minus h. H is very small number. X is 0 plus h, so we just go ahead. Okay. So left hand limit, that is x is less than 0. So you have to take negative x here, because you are on the left hand side of 0. So it is going to be minus x, negative x. So minus x, here you are going to take a positive x, of course. Positive x, the function is done. Now you can apply the limit. So x has to be replaced by minus h. So minus minus h is plus. And here you have to replace x by h. So you have a h. So limit h tends to 0. These are a limit h tends to 0. This is limit. So you have a h here and h here. Limit h tends to 0. So you get a 0 here. You get a 0 here. So it is continuous. This modulus function is continuous. But you can easily prove that it is not continuous, as we have done in the previous discussions also. So I want you to do it by yourself, but I will give you a reference also. You can just have a look here. If you have any problem, just have a look and refer to it, because we have already done. So I am just giving you a hint that it is, you will find it as not differentiable but continuous. If fx is differentiable at x equals to c, then write the value of limit x tends to c fx. So if it is differentiable at x equals to c, then write the value of limit x tends to c fx. Remember, just we did a question a few minutes back, and we proved a limit x tends to c fx is fc. We just proved it. Okay. If fx equals modulus of x minus 2, write whether f dash 2 exists or not. So we will just do the classical solution. So let us do it. Basically it is y equals x minus 2. It's a line. Okay. So x is 0, so y will be minus 2, and y is 0, so x will be equal to 2. So this is just a kind of line I am making. It is not actual line. Okay, I am just making a line. I am just saying that there will be no negative in the below y. It will go up. That's what I wanted to just tell you. So this f dash 2 is basically finding out the derivative at 2. So modulus is what? Fx, if modulus x minus 2 is there, it will be positive ahead of some value and negative below that value. When with y was modulus x, it was the 0 point, which was the point dividing the negative and positive value. When you have x minus 2, just put x minus 2 equal to 0, that is x equals to 2. 2 is the dividing point. All the values above 2 are going to be positive, and all the values below 2, they are going to be negative. So when x is greater than or equal to 2, you are going to get positive x minus 2. When x is less than 2, you are going to get negative of x minus 2. I hope you got this idea. So in order to prove, or in order to find out whether this f dash exists or not, let us find out the f dash using the classical left hand derivative and right hand derivative. The left hand derivative, right hand derivative, I'll just change minus x minus 2 to 2 minus x. So x is equal to 2. So x equals 2 minus h, x equals 2 plus h. So going on the left and right, that's what we are doing. So f dash x will be equal to fx minus fc by x minus c. Fx minus fc by x minus c. What is fx? When you go on left, this function you are going to use x less than 2. So it will be 2 minus x here. And what will be the value of f2? See, if you put, this is the equality sign, okay? So when you put f2 in x minus 2, it will be 2 minus 2, that is going to be 0. So I am placing 0 here, but let me tell you f2 is 0 divided by x minus 2. So 2, let us replace x by 2 minus h here. 2 minus h minus 2, so it will be negative h. And 2 minus, here also I am replacing it by 2 minus h by minus h. So 2 minus 2 plus h, 2 gets cancelled. You have h divided by negative h. So h gets cancelled, you get a negative 1. And please remember, everywhere you have to write limit h tends to 0. I'm not writing it, but you have to write it on every step. Now x greater than or equal to 2, so you have to use a function called x minus 2. So x minus 2 minus 0 divided by this, of course, x minus 2, so 2 plus h minus 2, you have h. In place of x, replaced by 2 plus h minus 2 divided by h, 2 gets cancelled, h gets cancelled, you get 1. So the limit h tends to 0, 1, limit h tends to 0 here, negative 1. So they are not matching. You can easily say that f dash 2 does not exist. Write the points where fx is equal to log base ex is not differentiable. Okay. So this we are going to discuss next time. Thank you so much. Take care of yourself.